OpenBDLM, what is it for? This is what we're going to look at together today. So the OpenBDLM project that you're seeing here, what is it for? So this main goal was to develop probabilistic data-driven structural health monitoring solution. So what we want to do first is to be able to separate what is the baseline behavior, so the behavior of a time series or a system without the external effect. So separating the irreversible from the reversible effect. As we can see here, we have a raw time series, and we want to separate this into what is its baseline and what is its reversible, in this case, seasonal effect. Second goal is to detect regimes changes, which are going to be an indication that there's an anomaly in a time series. As you can see here, we have a temperature time series. We have a first 0 speed regime to another constant speed regime here. And what BDLM allows to is here to detect a change in the probability of having our second model, the one with a constant speed, being the correct model. So we see here we have a close to 0 probability that it's our second model, and here we have this jump in the probability that it's our second regime that explains the data. And that allows us to remove here the observational noise from the baseline to be able to extract what is the behavior of our system over time while there are regime switches. Then what we can do is to model the dependencies between time series. So what we can see here is, for instance, the displacement of a structure over time. And here what we can see is the temperature surrounding that structure over time. What we can see here is that there's a negative correlation or negative dependency. What does it mean? When the displacement is high, the temperature is low. When the displacement is low, the temperature is high. So it's characterized by a negative correlation here. And we can use these two time series and analyze them and estimate them together. Another thing we can handle is missing data. For instance, here we can see that a large missing segment is present here in the recorded data on a system. So we can have either short-term or long-term missing data as it is here. And we can see that while applying this into BDLM, automatically we're going to fill the gap where data is missing without requiring any special treatment. And this still allows to detect, for instance, here, regime change or a jump in the time series. Another thing that we can handle with OpenBDLM is non-uniform or asynchronized time steps. As you can see here, for the dataset we saw previously, the time step length is not constant. So what you can see here on the horizontal axis is time. On the vertical axis is the time step length on a log scale in hours. So this represents here 10 hours. So in this case here, it's exactly 12 hours. And you can see here, it's about an hour. And you can see that at many different locations on that time series, we have different time step length. And OpenBDLM allowed to operate in these conditions, which are fairly common in practice. Moreover, if you're analyzing multiple time series, OpenBDLM will allow you to synchronize these time series so that they can be analyzed together. So BDLM, what does it stand for, is Bayesian Dynamic Linear Model. How does it work? So we're going to see how it works through this simple example of us trying to predict the trajectory of a projectile through time. So for instance, I want to predict the trajectory of this projectile over a sequence of time steps. So I know from Newton's equation of motion that this is going to be behaving as an accelerating behavior. So I can model this by a local acceleration component like this, where my position accelerates over time. So here, what I can do is, if I know my initial state, my initial position, initial velocity, initial acceleration, I can use this constant acceleration model to predict where am I going to be at time t+1 using the kinematics equation. And then what I can do is I can observe at time 1 what was my actually real position. And then what I can do probabilistically is to update, given my prior knowledge of where should I have been, my actual observation, I can update my knowledge of what is my position, my speed, and my acceleration. Then what I can do, repeat the same process. Predict for the time t plus 1, given my knowledge of the kinematic model, where should I be at time t equal 2? Then collect an additional observation. Update my knowledge of the position, speed, and acceleration. Predict again. Observe, update. Predict, observe, update. Predict, observe, update. So always recursively using these 3 key steps. Predict using a kinematic model. Observe what is my real state. And update my observe as well as hidden states. So this is the key basic functioning of Bayesian dynamic linear models, BDLM. So this local acceleration kinematic model is just one among many other building blocks that we can use in BDLM. This one is called local acceleration. So this is one, but we have other ones. For instance, if we have a constant speed model, this would be a local trend. If we have a constant behavior, that would be a local level. We can model as well some periodic behavior. So periodic for instance, a hourly, daily, seasonal behavior. So this is going to be our periodic block. And we have also autoregressive block to model phenomena such as model errors that are dependent over time. So this is going to be our autoregression or autoregressive block. And the strength of BDLM is that it allows to combine and to mix and match all those components together to create very diverse model in a very simple way that can model really complex and rich behavior. It can be adapted to pretty much any situation. So let's look a little more closely. How can we assemble these blocks together to model complex behavior? For instance, here we have the displacement over time of a system, okay? So here we can have a local level that is going to model here the average behavior or the average response over time, the irreversible response of our system. Then we can have a periodic block that's going to model here our yearly periodicity behavior. And we're going to have an autoregressive block that's going to model what is not captured either by the local level or the periodic, but is neither observation error. This is something like a residual term in our model that is time dependent. So if we apply this, we can separate this raw observed data into this subcomponent here, local level. So we can see the change in behavior over time. That is, in this case, constant. Then we have here the periodic behavior. So we have extracted simply the dependency over time, the periodic one. And here what we have is the residual term, which is the autoregressive component. So what BDLM allowed to separate this raw behavior, this raw data, into a superposition of hidden state that describe the reversible as well as irreversible behavior of the system. Then another thing we can do is to model dependencies between multiple time series. For instance, we have the same displacement we've seen previously, and now we can model this by a local level, and we're going to have two placeholders to represent the periodic behavior as well as the autoregressive, the time-dependent behavior. But these are placeholders. Why? Because the displacement we see here is actually caused by the change in air temperature that we can measure as well, and that is represented here. So what we want to do is to model and estimate simultaneously the response of both displacement as well as temperature. And here what we want to do is to create dependency between the hidden state of displacement and the hidden state of temperature. So in the case of temperature, we're going to have three blocks: a local level representing the baseline of the temperature, a periodic behavior to represent that seasonal effect, as well as an autoregressive behavior to represent a time-dependent component that are not modeled by these two other. And then what we're going to have linear dependency between these two blocks and these two placeholders representing the displacement here. So we're going to be able to see that if there's a change in temperature, it's going to directly affect our displacement in the structure that we're trying to model as well. Okay, now what happens if we're trying to model a system which has a change in the behavior over time, such as here we're modeling the temperature over time. We see here we have a 0 speed model, and here we have a constant speed model. So what we're going to do is that we're going to kind of estimate multiple models that are going to be at each time competing against each other. For instance, here we have the first model, which is the local level, representing the constant part here. We have a second model that represents the 0 speed here, constant speed here, second model. And for every time step, I want a system to automatically estimate what is the probability of either model. So this is what we're doing here. We see that in the first part, the probability that it's the second model, the constant speed model, is very, very low until I have a transition here where it becomes the dominant model. And as I said earlier, this is what allows us to separate the reversible effect and the observation error from the baseline behavior, which is here constant, which is here with constant speed. So we can do this in real time using real situations. Okay, OpenBDLM, what is it? It's a MATLAB platform where all these solutions we're developing for Bayesian dynamic linear models are implemented and openly accessible to the whole community. So there are three operating modes for OpenBDLM. First is interactive mode, where you're going to be able to interact with the interface in a dynamic way. How to access this is simply typing OpenBDLM_main to access it. If you want to retrieve some of the results as output, there are four possible outputs that you can retrieve. Either data, the model, which is going to contain the model structures, the estimated states, as well as some various options that are there to define your specific analysis. So this is the interactive mode where you're going to have multiple choice asked to you and you're going to have to return some choices with the interface. The second mode is from a configuration file. So rather than manually defining everything you want to do for your analysis, you can define this in a configuration file. And you can share this configuration file with other collaborators, for instance. And in this case, what you can say is that you can pass as input to OpenBDLM main a config file cfg_. You give it the name where all the specificities of your analysis are going to be predefined. And a third mode is the batch mode. If you want to process a large collection of dataset, you can do this in batch mode using OpenBDLM, where you're going to provide the config file you want to process, as well as what are the specific option or operation you want to do in BDLM. Okay, for instance, let's, for example, want to generate a configuration file and use it for the first displacement example we see, where we want a local level, a periodic component, as well as an autoregressive component. How do we do this? So the function call for this would be, okay, my output equal OpenBDLM main, and I give here my configuration file containing everything I need to define this model. How would this configuration look like? It would look simply like this. So I have, for instance, here the project name. You can name it as you wish. Then this is part A. Part B is for the data. So you need to load and store somewhere your data. In this case, data.value contains a vector of values for this time series. Data.timestamps contains the timestamps for each of the data point you have collected. And finally, you need to define a name for your time series. I've called it disp here. The third part is the model structure. Which block do you want to use in this time series for this studying this time series? In this case, we want to use 4 blocks. So here I mentioned I want 2, but why is there 4? It's because here we have 2 periodic components. So 11 is going to be the local level, the constant behavior, the irreversible behavior over time. Then I have 2 periodic behavior, one to represent the yearly periodic pattern, a second one to represent the daily variability that is at a much smaller time scale here. And finally 41, which is going to be my autoregressive block. So simply by calling this line OpenBDLM, we'll know that this is the block configuration you want to use for this model, and it's going to automatically create all the mathematical formulation for this model. Okay, and here you don't have any, you just have a single time series, so you don't have any dependency between several blocks. So here the intercomponent dependency is empty. So this is simply how you would define a configuration file for this case study. What if you have dependency between time series, such as what is illustrated here? So for displacement, you want two blocks, the irreversible local level, the autoregressive to represent time-dependent behavior. And you have two placeholders, and you want these placeholders to depend on the hidden states from the temperature, which consists in an irreversible behavior, a local level, two periodic patterns, one daily, one yearly, and another autoregressive pattern. So this is the function to call. This would be the configuration file. So project name data remains mostly the same, except that now in data.values, what you have is a vector or a matrix of two columns. First column is the first time series, second column is the second time series. Now in C, where we define our model structure, what we have is now in our cell array, we have two vectors. The first vector is for the first time series. The first block, local level, is 11. Autoregressive is 41. For the second block, what we have is 11, 31, 31, 41, which is local level, periodic yearly, periodic daily, and autoregressive. So this is simply how you would define two different time series that are dependent on each other. Now the last part we need to define is which time series depends on which one. In our case, it's the displacement that depends on temperature. So here in model.component.intercomponent dependency, we have the first time series, which is in the first placeholder, depends on the second one, so 2. And the second one depends on nothing, so it's empty. So this defines this two time series dependency. In general cases, you can have much more than two time series that depends on each other. Okay, what if you have a regime switching example? So we have a first model that represents here a local level, so a constant behavior over time. The second model that represents a constant speed model over time. So this is our function call. The project name data remains essentially identical. The model configuration now consists in two models. So we have model 1, we have model 2. So model 1 is the block 21. The block 21, what is it? It's going to be the local level compatible with local trend. The second block, the second model, is going to be directly 12, local trend. Here we have a single time series, so our intercomponent dependency is empty. So simply with this configuration file, OpenBDLM has everything it needs to build the mathematical model for this time series. Okay, so let's look at the global workflow of OpenBDLM. So if we start from raw data that's going to be stored in a CSV file, we have pre-processing tool to store, to pre-process, to maybe aggregate data over multiple time steps. So you can interact with the pre-processing tool, so the user interact with the pre-processing tool until the data has been correctly configured for the user. Okay, then the user say, okay, for this specific time series, what are going to be the building block I want to use? So the user define what is this, its model configuration. Then automatically OpenBDLM is going to build the mathematical formulation for the model defined by the user. When this is done, we're at the step of learning the parameters that are intrinsically associated with the model defined by the user. So we have two choices. Either we go from the interactive path of going from raw data, configuring the model using the interactive mode, and now we're at learning parameters, or we can bypass this step by directly loading into OpenBDLM a configuration file as well as its associated data. So either way are possible. Either we use the interactive mode or we directly bypass this and load a configuration file that's going to be analyzed by OpenBDLM. So when we're learning parameters using the pre-implemented gradient-based optimization algorithm, either Newton-Raphson or stochastic gradient descent. What we're going to do is that we're going to learn the parameters, and these parameters are going to be returned to the user, which is going to define, okay, if I converge, does everything seems fine? Yes, no, no. Let's keep optimizing again. If yes, I can carry on and estimate my hidden state, which means separate my raw time series into the superposition of many hidden states. Then these hidden states are going to be returned for visualization to the user, which is going to define, okay, does my result make sense? Are my result good? Yes, no. If not, I need maybe to redefine my model and rebuild it. Otherwise, I can carry on and export the results, either through figures, through a configuration file that I'm going to be able to either reload here or share with other users. A data file that contains all the data for my project. All in the project.mat, I'm going to have all the hidden states and all the figures I have created, as well as a log file that stores all the operations that were done since the beginning of the analysis. So the first part here is the loading part. The second one is the learning, where we're learning the parameters of our models. This is the filtering or estimation part, where we estimate or separate our time series into hidden states. And finally, we have the results that are either going to be used as saved file or presented as figures. Okay, here's example of real time series we can study with OpenBDLM. So here what you see is the flow rate in a dam over time. So here you have time, you have that flow rate. This is the data that was used to train the model. So we see we have an upward trend as well as we have an increase in amplitude over time in our behavior. So the training was stopped here, and here we're in full forecast mode, where the blue data here was never seen, never used by the model. And what you can see is that the dashed line represents the expected value predicted by OpenBDLM. The kind of gray shaded area represent the plus or minus 1 sigma confidence interval. And this forecast is the result of the superposition of the many hidden states. For instance, the local level, here the local trend, which represents the speed of change over time. We have here the irreversible periodic behavior, which we can see that as an increasing amplitude over time. This is the forecast value. And finally, this is an autoregressive behavior. This is the part of the model that cannot be explained, yet that is not just attributed to random noise. This is kind of our model residual term, what we cannot explain, which is fairly small in comparison with the raw data and even the irreversible behavior. So here's the first example. A second one, if we want to detect anomalies. What we have here is time, displacement in the dam, and on the second graph here, what we have is the probability of a regime switch. So the regime switch between the constant speed model and the zero speed constant speed model and a constant acceleration model. So here the peak indicates a high probability for the constant acceleration model. So by doing this, what we can do is separate the irreversible behavior represented here by the level, where we can see clearly that once we separate this, we see a jump in the behavior. And this jump is also accompanied by a jump in the speed of the system. We can see we had a constant speed here, we have a quick change in the regime, and we go back to a normal regime here, where the speed before and after the abnormal event are different. And we can quantify this in real time. So this was the level baseline, this was the local trend, the speed of change of the baseline. What we have here is the irreversible behavior, represented by a kernel regression component. We can see here, and what we have finally is the irreversible like residual term, what cannot be explained by the other components in the model. And we can see here that clearly we can easily identify what is the regime switch that correspond to an anomaly in this case. Third example, we have here the temperature recorded at Montreal Airport from 1953 till 2013. And what we want to see is we want to quantify what is the evolution of the rate of change in the temperature on the scale of this over 60-year period. Okay, so if we separate this raw time series in many hidden states, we can see here from the baseline behavior represented by the level that the temperature has decreased from the 50s till the 70s and then start to steadily increase. And we can quantify this increase here through the local trend, where we can see that in 2013, the rate of change of temperature was roughly of 2 to the times 10 to the minus 4 degrees Celsius per day. This is roughly 0.06 degrees Celsius per year. So we can see that from the 80s till 2010, we are steadily increasing in temperature at a rate of roughly 0.06 degrees Celsius per year. So we can see that from these raw data, we can extract knowledge by separating the baseline behavior of a time series from its irreversible periodic patterns here and the autoregressive term that represent the part that we cannot explain with our other components. So to conclude, OpenBDLM is an open source platform that was released in May 2019 that allowed to process time series. So if you want to know more information about how does it work, how can I get started, go on our YouTube channel, what you're currently probably looking at, in order to see all the other videos of tutorial where you can see how can you use it quickly for your applications. So what's included in OpenBDLM is several pre-processing tool, data loaders, time synchronization tool to go from your raw data into a structure that you can use with OpenBDLM. So through every step of the process, OpenBDLM will support you in these steps. Then for OpenBDLM, there are 3 operating modes, either interactive, where the user interacts with the interface. There's a second one, which is through configuration file, predefined model you can directly load into BDLM as well as share with other collaborators. And finally, batch mode, where you can process large amount of time series through a completely automated process. So OpenBDLM is automated. What do we mean by this? All the model construction phase. So once you define which block you want to use, all the step of building the mathematical formulation associated with these models is fully automated. Then the parameter estimation is already pre-implemented in OpenBDLM with many optimization algorithms, Newton-Raphson, as well as several types of stochastic gradient descent methods. And same thing for state estimation using either Kalman filter, UD filter, as well as smoothing algorithm. We also offer several post-processing tools to either export the result in data files as well as create plots that are publication ready that you can either export in PNG, PDF, or in LaTeX format. So if you want to know more, go on our YouTube channel and look at the many tutorial and video we're providing to getting you started with OpenBDLM.